Okay. Well, thank you all for coming. Thanks very much to Manu for inviting me to speak here today. I'm a climate scientist, and most of my work focuses on drought. And in particular, I have a keen interest in trying to understand how drought risk and drought severity will change in a warming world. When we look to the future, the main tool we have to do this are climate models. And so we can go to the climate models and we can see, for example, what soil moisture does in response to various warming scenarios and use that to inform our understanding of what the future might look like. A really good example is in the summary for policymakers from the latest IPCC report. What you're looking at here is basically an ensemble average of CMIP6 climate models showing changes in total column soil moisture under a 2-degree warming scenario. And as you can see across this particular map, all those brown areas are areas where soil moisture is expected to decline in response to warming, and this translates to increased drought severity and risk. Now, the problem with this, though, is that drought is messy. It's an incredibly complex phenomenon that depends on a variety of different interacting physical, biological processes that all affect how drought manifests across the hydrologic cycle and at the land surface. To have confidence then in these model projections, we need to have confidence that the models are resolving all of these processes to a reasonably good level. That can be kind of a tall order, and that's the reason why many people, myself included, approach the model with some degree of skepticism. So ultimately, for a more comprehensive understanding of drought, we can bring in other sources of information. Of course, we can bring in the observations, but I would argue that the observations themselves are actually kind of limiting. Drought is by definition an extreme event, which means that it's going to be rare. So the sampling over the historical observational period is going to be limited. At the same time, even within that period, we see outlier events that are hard to reconcile with our general understanding. A really good example is shown in the figure right here, which is the Dust Bowl drought of the 1930s, which doesn't really look like any other drought in the US in the 20th century. So the argument I'm going to make today is that we have another source of information that can provide a lot of insight, I think, into drought dynamics and how drought will respond in a warming world, particularly when we combine that information with informed use of climate model simulations. And that is the paleoclimate record. And so today I'm going to talk about really a decade's worth of work that I've done and participated in this regard, and try to showcase and hopefully make the case for you that we can use paleo information, again, with climate models to inform our understanding of what caused major drought events of the past. We can use it to understand a little bit about what role climate change might be playing in drought events happening today. And we can also use this paleo information to constrain and develop a better informed understanding of what the models are telling us should happen over the 21st century. So we're going to kind of start in the past and work our way progressively through the future, focusing primarily on Southwestern North America. Before that, though, I think it's worthwhile to introduce the data itself, right? So there's a lot of different sources of paleoclimate information. And the one source that I'm going to be focusing on are tree rings. Tree rings provide a few advantages if you're interested in high-resolution paleo, basically the last 1,000 to, in some cases, 2,000 years. One, there's lots of trees all over the place, so we can actually use trees to inform our understanding across a lot of different regions. This is just one snapshot of the International Tree Ring Database, and all those green triangles you see there are contributed chronologies and data sets. And so you can see that at least outside of Africa and the deep tropics, we've got quite a bit of information that we can use to work with. Additionally, trees, at least the trees that we use for these types of reconstructions, are annually resolved with effectively zero dating error. What this means is that we can identify events happening in specific years and relate them to other things in the paleoclimate record or for the overlap of the observations, specific observations. This makes it more straightforward to kind of generate quantitative reconstructions of whatever we're interested in. The trees themselves, how much ring growth they typically put on, typically depends on the growing conditions that they're sitting in, right? So if there are good conditions for growth, the tree will be very productive and will oftentimes put on a wider ring, shown right here. But if it's dealing with a bad year where growing conditions are not so good, then they might put on a narrow ring right here. And each one of these, sorry, just to clarify, each one of these light and dark couplets is a single year of growth. Now, What makes good or bad conditions? Well, it really depends on the trees, depends on the location, but generally speaking, at least across many, many areas, what they care about primarily is water. The figure right here is from a paper by Scott St. George from a while ago, but every triangle you see right there is a different tree ring record. And the color there shows the correlation with winter precipitation at the top and summer precipitation at the bottom. And what you can see is that over much of in this case, the northern hemisphere, there's a lot of red here indicating strong correlations between tree growth and either wintertime precipitation that carries over into the growing season as soil moisture or summertime precipitation. We can basically kind of combine all this information together through the kind of typical target for tree ring reconstructions, which is summer or growing season soil moisture, oftentimes represented by drought indices like the Palmer Drought Severity Index. And that's what a lot of people have done over the years, and that has led to these large-scale, spatially resolved data sets of soil moisture that cover effectively wherever we have these tree ring chronologies. This is just a paper, or this is just a figure from a recent paper that I just put up here to kind of show where we have this information available, right? And so this is a kind of amalgamation of all the different drought analyses together. In this case, we're just showing the autocorrelation, but you can see that we're covering pretty much the entire northern hemisphere, outside the tropics, eastern Australia, New Zealand, and southern South America. Now, I'm not the first one to have used this information to study drought in the climate system. A lot of people have done this. One of the very common uses is to kind of compare recent events that seem extreme against the kind of full range of the paleoclimate record, right? And so I've done some of this with other people, looking at, for example, the recent drought in the Levant region, the Eastern Mediterranean, the Chilean, Argentina recent drought shown right there. And then also just looking at recent events in Australia and New Zealand. One of the most important things that's kind of emerged from studies of these large-scale reconstructions has been this phenomenon called megadroughts. And you may have kind of heard this term, oftentimes used in the newspapers and in public media. There's no real kind of formal definition, but we kind of offer this definition that a megadrought is really an outlier drought, a drought that's really persistent, or stands out in terms of its severity, duration, or spatial extent compared to recent drought events. And what we can see, and this again is, I think, highlighting the importance of looking in the paleo record, is that pretty much everywhere around the world over the last 1,000 years has experienced a megadrought that we wouldn't know about if the only thing we had was the actual observational record to look at. And that's kind of highlighted in the figure right here. And anywhere in the kind of green circles, these megadroughts have been documented specifically in the tree ring record. In the Central America and in much of Africa, we don't have the trees, but we have other information that suggests these particular events. So now what I want to do is kind of zoom in a little bit on Western North America and talk about some of the work that we've been doing over the last 10 years to, again, kind of leverage the paleoclimate record and inform our understanding of drought dynamics in this region. And a lot of what we're going to do is kind of leverage one of the latest reconstructions. So this is just a soil moisture reconstruction for southwestern North America, effectively the four corner states, California and Nevada. This is a standardized Z-score going from 800, in this case, up to 2023. Negative values indicate droughts. Positive values indicate wetter than normal years. And I've highlighted in the red stripes there all the droughts that are over 10 years. And so you can see here some of these mega droughts that we've been talking about. Some of the ones that really stand out are this late 13th century mega drought from the 1270s up through the 1290s. This was actually the drought that coincided with the collapse of the ancestral Puebloan populations and the abandonment of Mesa Verde in the Four Corners region. The other really notable event was this late 16th century mega drought in the late 1500s. And this was a really intensive, massive drought that affected not just the southwestern US, but actually much of the Central Plains as well. And this event is actually recorded in Spanish colonial records at the time. Now, one question is, we have all these mega droughts in the past that we've documented. Well, what is the possible cause? And here's where we actually have to, as much as we may or may not like to, actually start to leverage some of the information provided by the climate models. Because at least in this particular case, we've got this great reconstruction, at least I would argue, of soil moisture variability over southwestern North America, but we don't have the other information from it that we need to understand the dynamics or drivers of these particular events, right? We don't have, in this case, a reconstruction of ENSO or the jet stream that we could compare against. But what we can do is we can kind of take this and use this to kind of inform our approach to using climate model simulations and ask, for example, can climate models actually generate megadroughts like what we see in the paleoclimate record? And the answer is many of them can. So what we're looking at here is on the x-axis, we have droughts of different lengths. On the y-axis, we have drought severity, which in this case is just the cumulative soil moisture anomaly during that drought. The different dots there represent the results from different model simulations. These are all simulations of the last millennium or the pre-industrial period. And then the X there is the reconstruction. And so there's differences across models, of course. But what we do see is that there's at least two models, in this case, CCSM and IPSL, that seem to generate droughts of similar lengths and similar magnitudes to what we actually see in the observations, or at least in the reconstruction here. And that's in the purple and the blue dots we see there. Now, if we kind of take this kind of as these kind of events as kind of analogs, what we can then do is dig further into these climate model simulations and see, well, what were the ocean atmosphere conditions within these simulations that were able to generate these megadroughts, and kind of use that as a way to inform at least a hypothesis from what might have driven these particular extreme events. Now, in the two models that do a pretty good job at reproducing the kind of spectrum of drought variability that we see in the observational record, these models, the kind of association with megadrought, or there's a strong association between these megadroughts and cold tropical SSTs in the eastern tropical Pacific, so-called La Nina states. And that's shown right here. So, these at the bottom here, these are all just different indicators of ENSO. So, for example, the Nina 3-4 index or the tropical Pacific gradient mode. And then on the y-axis here, just looking at the kind of percent occurrence during megadroughts in these models of either the drying mode La Nina or the wetting mode El Nino. And then the colored dots are the ones that the association is significant in its statistical sense. And so we see kind of at least the CCSM model and the IPSL both stand out there with this strong association with La Nina events. Probably not coincidentally, these are also the two models that have the best teleconnections and most stable connections with the actual with the tropical Pacific compared to the observations. And that's what's shown here. So we define the teleconnection as simply the correlation between Nina 3-4 index and the 500 hectopascal geopotential heights across North America. And then we just calculated pattern correlations between these models and that kind of observed pattern to see kind of how stable it was and how well it does. And so you can kind of see right here, very high correlations with a very narrow range for these two models that show this strongest association with La Nina. Whereas other models, like for example, Barak or MPI, you can see the correlations, the teleconnections are much weak and much more unstable. Now, in this particular application, we're using kind of independent reconstruction of climate, independent model simulations, kind of identifying analogs and trying to put together a story there. But there are other approaches as well. And this is something that we did with a new postdoc, Nate Steiger, a few years ago, and that is take a kind of data assimilation approach. It's becoming kind of increasingly common to generate what are called less millennium reanalyses, effectively simultaneous reconstructions, not just of the climate system, but also other information on what the climate system is doing that could allow you to better connect things like drought events to particular dynamics. In the case of ours, this is the FIDA. And effectively, we use as our, we sample our prior from the simulation of the Community Earth System model, the CESM. We use years from there to set the prior, and then that prior gets updated based on the proxy information that gets assimilated. So really what this is fundamentally doing is we are constraining the spatial covariance of fields like soil moisture or sea surface temperatures using the model And we're constraining the temporal evolution based on the proxy records that we're using as part of it. And so again, what the advantage here over the previous approach is this allows us to kind of put together all the information together at the same time, and then do a similar type of analysis to ask, well, can we get these mega droughts, and what are the conditions associated with these droughts that could explain them? The basic result is shown right here. So this is from the reconstruction. It's an ensemble reconstruction. So this is the ensemble average. We're going from 800 to 2000. The red line there is the green line there is the Niño 3-4 part of the reconstruction. The blue line is the Atlantic multi-decadal oscillation index, basically an indication of tropical North Atlantic SSTs. And again, I've just kind of highlighted here what this reconstruction gives us in terms of the megadroughts in the background kind of salmon bars there. And overall, the FIDA actually does a pretty good job compared to other reconstructions at reconstructing drought over North America. Picks up the similar events such as that late 13th century megadrought and the late 16th century megadrought. But now we're also getting simultaneous information on some of the drivers that we can now use to compare and again see if our story still holds up using this alternate approach. And largely it does. So there's a few ways you can do this. A little different ways you can approach this analysis. But in this case, all we've done here was this figure right here shows the beta regression parameters, bootstrapped beta regression parameters for logistic regressions, where effectively we're just using, in this case, the Niño 3-4 index and the AMO index, either with volcanic eruptions or without volcanic eruptions, to predict the occurrence of megadrought years. And what this shows is that in the case of Niño 3-4, 99 or 97% of those beta regression parameters are negative, indicating a strong association between these megadrought years and La Nina conditions in the eastern tropical Pacific. Similarly with the AMO, there's a strong association between these, not as strong, but a significant association between these megadrought periods and warm SSTs in the tropical Atlantic. And to be clear, the kind of results we're getting from here, are all kind of consistent with our understanding of kind of the dynamics that people have developed over the last several decades. So there's nothing here that's kind of outside of maybe expectations, but again, it's providing evidence that we can get these exceptional ocean states that can give us these exceptional droughts, like we see in the paleo record. The FIDA itself is a fully spatial reconstruction, and so we can kind of dig a little bit deeper. The background SST patterns you see right there are actually self-organized maps, and I show this because these are the two SOMs that have the strongest association with megadrought periods in the FIDA reconstruction. So pattern 1 is 51% more frequent during megadrought periods, and pattern 2 is 161% more frequent during megadrought periods. And then the shading over the land is basically the kind of composite during megadroughts in the southwest of the soil moisture indices. So you can see the strong drought there over southwestern North America, but you can also see within the FIDA, it's also producing droughts in other regions that are consistent with the full tropical Pacific SST forcing, including places like Southern Africa or East Africa, where we actually don't really have much paleo information in the FIDA. Wetter conditions over Australia and Southern and Southeast Asia, and drier conditions over extratropical South America. Okay, so moving from the past to the present, we can also use this information to, I think, inform a little bit more about what's going on now. So you're all in Arizona, you're probably very familiar with droughts, and you're probably very familiar with this early 21st century megadrought that, at least by some metrics, seems to have recently ended. Kind of peak of the drought itself was from about 2000 to 2021. And the first and most maybe basic thing that we can look at is simply ask the question, well, how does this 22-year, in this case, drought period, compare to all possible other 22-year periods going back 1,200 years? Does it really stand out, or does it kind of fall within the kind of what we might consider normal range of soil moisture variability? So let's look at that. So how does this recent megadrought compare to past events? So here what we've done is we've just taken effectively the driest 22-year periods in the reconstruction, and that's what each of these colored lines means over the years that are shown right there. And we're simply calculating the cumulative soil moisture anomaly from the year it begins out to the last year. And so let's just kind of look at what the driest events are and see where this current 21st century megadrought actually sits. Well, the third driest here was that late 13th century megadrought, again, that one that caused the abandonment of the Mesa Verde settlements. The second was this late 16th century megadrought. And then at least by this particular metric, 2000 to 2021 really does stand out, at least in terms of this soil moisture, as the single driest 22-year event of the last 1,200 years. Now, this brings up the next obvious question. Well, was it so dry because of natural variability, or did climate change play some kind of role? And so this led to us to do some detection attribution work. Now, again, I know many people are skeptical of models, but it's very difficult to do any kind of detection attribution without models. And so here we used models initially from CMIP5 and then from CMIP6 to estimate what the kind of forced soil moisture response in the region should be. We could then subtract that from the observations, generate a counterfactual soil moisture, and compare the two to get some kind of evidence for, or get some kind of estimate for what the contribution was of climate change to this particular event. So this is the first study we did that came out in 2020. At this point, we were just looking at 2000 to 2018. The black line you see right there is the observed drought, in this case just expressed in terms of trailing 19-year running means. Okay, and so this is the kind of peak of the drought right there, right? The orange line here is effectively the ensemble average from the historical simulations from CMIP5 of soil moisture. And so kind of excluding any kind of natural variability, collapsing down to the singular forced response. If nothing else was going on, this is what soil moisture would probably look, or that's what the models say soil moisture should look like in the southwestern United States or North America. As you can see that this drying trend kind of beginning towards the end of the 20th century. This drying trend specifically in the models is being driven primarily by warming-induced increases in vapor pressure deficit and evaporation that is steadily drying the things, or the soils. We can then subtract this climate change effect from the observations and generate our counterfactual, which is green there, which in this case we're viewing as what the drought would look like in a world without any kind of climate change. And then by comparing the two, we can get an estimate of what the actual contribution is. And so you can do this in a few different ways and test its sensitivity. For example, we looked at, we incorporated a CO2 kind of water use efficiency effect into the potential evapotranspiration calculation. But across the approaches, we get a kind of range of estimates between about 30 and 46%. So about 1/3 to about 1/2 of the magnitude of this drought, at least from 2000 to 2018, is attributable to climate change. We updated this in 2022, extending the analysis through 2021, and we got a very similar result of about a 43% contribution. Now, what does this mean? Well, it means that even in the absence of climate change, southwestern North America would have been experiencing a significant drought, right? And that's seen here by the blue line here, which is that cumulative drought severity absent the climate change signal. But it was really climate change in this case that turned what would have been a serious but more moderate drought into probably the worst 22-year period of the last millennium. Okay, so we've talked about the past, we've talked about the present, and now we can talk about the future. Right? And here's where we can again use paleo information to inform the analysis, including what kind of events we might want to look at, but also use it to constrain the models or understand the models and maybe some errors and issues that we need to maybe be aware of when we're kind of interpreting the response that they're giving us. So first, though, let's start with the models and just look what the models are doing, right? And so here we're looking at, this is from an ensemble of 18 models, and here we're just looking at precipitation, differences between the end of the 21st century, the end of the 20th century. In this case, we're looking at winter at the top, spring at the bottom under this SSP 370, which is a kind of high warming scenario. But as we'll see, we've done this as well for low and more moderate warming scenarios as well. And what those latest generation of models tell us is what they've been telling us for probably about 20 years now, which is that winters in the West are likely to get wetter in terms of precipitation, so increased precipitation. And springs are likely to get a little bit drier, with some areas of pretty large uncertainty where the models are giving us very non-robust results or very little agreement, highlighted by the shading you see right there. Okay, so that's the kind of first part of the equation for thinking about soil moisture drought. The other side, of course, is demand. And that is largely set by the vapor pressure deficit in the atmosphere. And if we get something very different, we get much more robust, much more uniform responses in the vapor pressure deficit compared to precipitation. And the reason for this is that the vapor pressure deficit just scales incredibly strongly with temperature. Right? And so across pretty much the entirety of North America, especially during the summertime, we're seeing that with warming, we're just getting big increases in the vapor pressure deficit. So we've got the supply, we've got the demand, and then we can look in the model and actually look now at the soil moisture response itself. And so here's the 200 centimeter soil moisture, which is what we're reconstructing. And generally, what the models are showing is that over the region, in aggregate, with pretty good agreement, over our southwestern North America box, the changes in precipitation and the changes in vapor pressure deficit are driving an overall drying in soil moisture. And you can kind of see that in all the brown areas right there. Now, we obviously don't have observations of the future, so we can't really compare this directly to our reconstruction or our observations. But we can compare the historical period against the observations and reconstruction that we have. And that's what we're showing right here. So each one of the colored lines you see right here are the ensemble averages for different scenarios. So the historical period, our 2.6 low warming scenario, 4.5 moderate warming scenario, 7.0 high warming scenario. And then the black line in the background is the reconstruction and observations of our soil moisture index. Of course, the variance in the reconstruction is much, much higher. And that's, of course, because you're kind of collapsing the variance, which you average across all models. But we can look at, for example, the 20th century trends and see how consistent they are or not between the models and between the observations. And generally speaking, we do see this kind of drying trend in in the models and in the observations. But we can look at that quantitatively, of course. And that's what's shown right here. So here we're looking for 3 different time periods, 1901 to 2020, 1950 to 2020, and 1980 to 2020, the soil moisture trends. Each black dot you see right there is an individual model, and then the red there is our observation soil moisture reconstruction. And so for most of the 20th century, either for the whole 20th century or for the latter part, the observed trends that we see in the observations are kind of sitting within the range of what we see from the models. For the more recent decades, however, it's really interesting because the observations actually fall far outside the range of what the models are telling us should be happening. Part of the reason for this is that this period from 1980 to 2020 represents a shift between maybe one of the largest pluvial events of the last millennium in the 80s and 90s into this really extreme megadrought. So, maybe we won't fault the models quite so much for not quite getting the this kind of exceptional series of events there. But at least, we have this information and we can kind of, use this to judge the models. Okay, so how then to kind of use all this to kind of look to the future? Well, in this particular study, we decided to look at analogs. So we said over the last 20 years, what's the worst single drought year? And what does that look like in the future? Right? How does the risk of these sorts of events look like at the end of the 21st century? So in this case, we looked at 2002, which was the single worst drought year from 2000 to 2021. It's actually the 9th driest in the entire record, so really quite extreme. Okay. And so we can kind of then look to the models, right? So here, each one of these kernel density plots is the distribution of soil moisture from different scenarios. So all the models, all the years pooled together. The gray shading in the background is the historical period, 1851 to 2020. And then the blue, orange, and red represent the 2071 to 2100 period under these different warming scenarios. I've highlighted here where 2002 sits. And then we're just going to take a very kind of simple, straightforward approach to estimating risk by focusing on the tail right here. And just simply say, well, how often do you get years under these different conditions, under these different ensembles that equal or exceed 2002? And we'll use that as our simple estimate of risk. But what we can do here, of course, nicely, is we can compare, for example, the historical risk against the observations, see how similar they are, and use that in some ways as a way to maybe judge the models. So the risk shown right here. So this is the risk percent on the y-axis, and here we're looking at our observed reconstruction, our historical simulations, and then all of our SSPs. And so one thing that was least encouraging was that the risk in the historical part of the simulations was very similar to what we see in the actual observations. So that was kind of encouraging. And then, perhaps not surprisingly, what we see is that under different warming levels, the risk increases kind of in concert with this mean state drying that we see in the projections, and that this risk tends to scale pretty well with the actual warming that we see. In this case, just how often this event happens in the simulations. Yes. So in this case, it goes from, in the observations, again, a kind of event that is the 9th driest in the entire 1200 year record, to under the highest warming scenario here, a 1 in 4 year event. Okay, so we can look at these single year analogs, but we can also look at the kind of long-term events. So if we're interested in these kind of long-term mega droughts, we can also see how often we get 2021 or 21 year periods with a drought magnitude equal or exceeding this early 21st century mega drought that we see right there. So we can kind of do the same exact analysis. And here's maybe where we start to become a little bit more concerned with what the models are telling us. So here are those same distributions. And of course, many of you are probably immediately focusing in on this weird kind of bimodality that we see there. Don't worry, I'm going to talk about it. But again, we can at least do their kind of risk calculation the same way as we did before and see what it tells us. In this case, it tells us a couple things that are not consistent at all with our analysis of just that singular year event. So one, it's pretty clear that the risk in the historical part of the period of the simulations is way too high, much higher than what we actually see in the observations. Again, this is in this case, the single driest 21 year event, the actual reconstruction, but you can see you get it much more frequently in the historical simulations. We're not sure why. It could be related to the low frequency variability in the models. Models often have a lot of difficulty generating realistic spectrum of variability in, for example, the ocean, and that can obviously affect the kind of manifestation of events on land. The other strange things is that, yes, we see an increased drought risk under the different warming scenarios, but there's nowhere near that same scaling that we actually saw with that singular year event. Well, and the reason for that actually lies in this weird kind of bimodality, right? What we actually found was that the difference or the spread across models within different scenarios is actually larger than the differences between the different scenarios, which is a very odd thing because generally speaking in model projections, the scenario uncertainty is the dominant source of uncertainty at the end of the 21st century. So we dug into our ensemble, and what we realized is that you could actually kind of separate the ensemble into two different sub-ensembles, kind of low risk ensemble associated with these peaks, or sorry, the high risk ensemble associated with these peaks, and a low risk ensemble associated with these peaks, and actually dig in there and see that a lot of the differences here is driven by uncertainty and precipitation. So here we're looking at MAM precipitation for the kind of the 9 high-risk models on the left, the 9 low-risk models on the right. And one thing that becomes very apparent is these higher risk models that are giving us much bigger increases in megadrought risk. There's much more robust soil moisture or precipitation drying in the spring compared to the low risk models. At the same time, the low risk models are also benefiting from more robust precipitation increases during the summertime. And that you can see kind of right there. Now, is there a reason to believe one over the other? No. But you know, I think what this shows is the importance of really, like, you know, even if we can't reduce the uncertainty, we can at least understand the uncertainty and use that as a way for you know, informing our interpretations. Yes, Mike.
So I'm lost at one thing, which is, since the models don't have appropriate low frequency variability, I would think that they would have much lower risk of a 22-year event happening than a 1-year event happening. But you're getting the opposite result from that. Any thoughts?
Yeah, I mean, it's the answer is I don't.
The only way you can answer that is they're just trying the whole bloody time, right? So
yeah, I mean, I know, and I think that's what. So one of the fundamental problems in the CMIP models is the tropical Pacific response in all the models looks nothing like the actual observations. And Richard Seeger's done a lot of this work suggesting that it kind of shifts into this state that, I mean, kind of warmer state with a weakened gradient that we don't actually see in the observations.
you end up not getting the wet years in the model. That's the problem.
Yeah, I think that's probably part of it. I mean, the other thing to keep in mind too is that, you know, we're looking at 200 centimeter soil moisture across all these models, but the land surface models are a garbage disaster in all these models, in the sense of, like, they're all very highly parameterized, they're all doing things very differently, they're all treating the vegetation in different ways. And so there's going to be large uncertainties there as well, including in how these sorts of things manifest at the drought. So it's probably this whole kind of cascade of things. You know, I was just kind of mentioning the low frequency variability because that's something that we've noticed in kind of other. Okay, so the final thing I want to discuss is kind of where I'm looking to the future, right? And one of the most important uncertainties in terms of drought and really any kind of summertime climate extremes in the future are the dynamics. Right? There's a lot of work trying to understand whether things like ridging events or certain wave number patterns will get more frequent or more persistent in a warmer world. And there's a lot of mixed evidence for that. One of the weaknesses here, I think, is the fact that we just simply don't have a really good, long record of the fundamental dynamics, especially up in the upper atmosphere. But what I'm going to try to argue, and something that we've been kind of working on with a few studies of the previous years, is that this is information that we actually can either target or, in some cases, even recover from past drought reconstructions. And so if we can then kind of use these long-term reconstructions to develop, you know, multi-century or even millennial length estimates of this kind of dynamical variability, that can provide a really important kind of baseline within which we can better contextualize what we're seeing happen today and thinking about the model projections of the future. So I'm just going to show a couple studies of kind of where we're kind of digging into this. One is for the Central Plains, where we actually work led by a postdoc, Casey Bowles, actually developed independent reconstructions of soil moisture and a ridging index for May, June, July. The interest here was really to try to understand those kind of late spring, early summer drought events that can oftentimes come on very quickly in the Central Plains. And so we were able to kind of develop these 500-year reconstructions of soil moisture right here, ridging index right here, both in standardized z-scores. Again, independently developed from different tree rings series. And what we find, again, unsurprisingly, is that there's a strong association between soil moisture drought and these ridging events. So these are just soil moisture distributions, in this case for ridge events, which we're defining here as just -1 sigma events in the ridging index. So now we have this kind of background data, and now we can actually look in the models and we can say, like, okay, well, you know, how well do the models reproduce these relationships? What do they show for ridging, but also what do they show for the impact of ridging on soil moisture as we move into the future? So first, the kind of model evaluation. What we're looking at here are the ridge index correlations. So basically the correlation, so we basically we calculated the soil moisture, same soil moisture index in a bunch of different climate model ensembles. We calculated the same ridging index. And here we're just showing the correlation for each of those models between the ridging and the soil moisture. The observed correlations about 0.5, right? So significant, but maybe a little weak. And the models, generally speaking, are a little bit weaker, but maybe not so weak that we need to throw them out. So, all right. So then we can kind of look in these models and just say, okay, first, are we seeing, do the models say that ridging should increase in the future? And the answer is yes and no. So some models, in this case, Access ESM15, shows a shift towards actually less ridging towards the end of the 21st century. So here we're looking at the ridging index from this model ensemble for 3 different time periods, 1851 to 1950, 1985 to 2014, and then 2071 to 2100. Right? And this is just the pooled ridging index. This is under the 245, so moderate warming scenario. And this particular model, the specific model, shows this shift towards significantly less ridging. But other models like IPSL actually shows this shift towards more ridging. And in fact, if you look at, these are the only 2 models I'm going to show, but you can look across all the models and there's no real consistency. Some models show no response at all. So it's all kind of a mixed bag and just kind of reinforces, I think, a lot of the uncertainty that we have and how these dynamics will change with warming into the future. But the one thing that's kind of interesting is that pretty much all the models show this shift towards a stronger soil moisture response when ridging actually does occur. So here's one model here, which is the CAN ESM5 model. The gray, what we've done here is these are distributions of soil moisture sampled specifically for ridging events from different time periods and from the reconstruction in the background. So that's the interquartile range of the reconstruction in the gray background you see right there. And what you see is that a ridging event, for example, in the model in the kind of pre-industrial period in the blue, will give you an anomaly of about -0.5 sigma. But as you move to the end of the 21st century, those same ridging events are going to give you about a -2 sigma, so a much, much stronger drought event. Now, you might say, and you'd be totally right, well, this is a model where the mean soil moisture dries, so this just reflects an overall mean shift towards drier conditions. But we also see this in the models where there is no mean drying. So this is our IPSL model, okay? And so all the dots you see over the central plains there indicate that the soil moisture response is not robust, not really getting significantly wetter or drier. And again, we've just kind of composited over the soil moisture during the ridging events. And if you compare the blue to either the red or the orange, you can see that the red or the orange under high warming levels all show, in this case, significantly drier soils during ridge events than during the pre-industrial period. And this highlights something else that we're kind of interested in, which is not even necessarily, are these dynamics changing, but is the impact of these dynamics actually changing? Okay, and then the final thing I wanted to talk about was a paper we just published, looking at a new kind of reconstruction across Eurasia and seeing if we could kind of pull out the dynamics associated with concurrent spatial extremes. In particular, focusing on one event, which is was the event in 2010, which was this concurrent heat wave and drought in Russia and extreme rainfall and flooding in Pakistan. This is, so here we're looking at the seasonal average maximum temperature from 2010 and precipitation. So this is kind of what that looked like at the scale. We were able to show that this is actually reflected in the soil moisture. In this case, the Palmer Drought Severity Index, but you can see it in other soil moisture data sets as well. So you can see the kind of drying over Russia associated with that heat wave and those wetter overall soil conditions over northern Pakistan. So the first thing we did was simply went into our large-scale reconstruction, which covers all of Eurasia, and composited events where that basically looked like 2010. So in this case, we just said, well, when does soil moisture drop below -1 sigma in Russia? When does it go above 1 sigma in northern Pakistan? And that gives us a composite map that looks like this. This itself is a very rare event, so it only occurs about 31 times over the last 1,000 years. And there's other ways you can kind of do this, but for brevity, I'm just focusing on this approach. But then what we wanted to do was see like, okay, well, can we use statistical techniques to decompose the drought atlas and recover maybe some of the dynamics that are known to have driven this particular 2010 event? So for this, we did a rotated EOF analysis. We tried a variety of different approaches, but this seemed to come out the best. And we found really two EOFs, two modes that seem to correlate very strongly with what's happening in these regions. So this is our EOF number one, which over the entire domain accounts for about 8.6% of the variance. This EOF loads very strongly over northern Pakistan, as you can see right here. The correlation with soil moisture over this particular region is about 0.9. And if we then take this principal component, associated principal component, and correlate it with some dynamics, we actually see evidence for a wave associated with this EOF. So on the top here is just our principal component time series correlated over the instrumental period with the 20th century reanalysis, 300 hectopascal meridional winds. And what you can see here is the kind of correlation pattern that looks a lot like a wave pattern identified by Schubert et al. In 2011, in which he was looking at, in his case, 250 hectopascal meridional winds to try to understand a little bit more about the summertime dynamics across the northern hemisphere. In the case of Western Russia, the fifth REOF is the one that seems to load most strongly, negatively correlated by about minus 0.68. And this PC was actually strongly correlated with 300 hectopascal geopotential heights, much more locally centered over northern Europe. And this coincides really nicely with the observations that we saw at the time of this kind of ridge event setting up over the region. And again, looks very similar to some of the patterns that Schubert et al. were kind of pulling out. You can basically use these two EOFs, and they're very kind of predictive of whether you're going to get one of these weird, wet Pakistan, dry Russia compound extremes. X-axis, each one of those dots there is a single year from our large-scale reconstruction. On the x-axis is our first principal component. On the y-axis is the fifth principal component. And then all I've done in here is just kind of highlighted the red years here, which are those years with those concurrent extremes. And you can see that in pretty much all cases, to get them, you really need the kind of positive phases of both of these principal components to kind of all come together. So at least, this is not the kind of, I would never say that this is the kind of definitive analysis of these sorts of ideas. But I think it's really encouraging because it really does highlight that, within these spatio-temporal reconstructions, there's a lot of potential to extract information about some of these dynamics because these dynamics have such preferred spatial fingerprints that are expressed in the soil moisture on the reconstructions. Okay, so just to finish up, I'm a paleo evangelist. Okay, I think it's underutilized. I think there's a lot of information we can use, and I think there's a lot of applications. Whether you're concerned about what happened in the past, what's happening today, or what's happening in the future. Again, I know a lot of people are skeptical of climate models. Believe it or not, I am too, even though I use them all the time. But that's why I think when we combine climate models, which give us some information about the physics, and constrain them with paleo or observations, we can leverage the complementary source of information and really generate deeper and more insightful understandings of some of these dynamics. And I really do believe there's still a lot more information that we can get from these reconstructions. And even now I'm working on proposals with postdocs to fund some of this work, specifically to try to tease out a little bit more about the dynamics underlying these extreme events. So thank you, and of course I need to acknowledge all of my collaborators who I've been working with for years now, and are obviously critical parts of all this work. Thank you.